Galileo once famously said that the universe cannot be read until we have understood the language in which it is written and become familiar with the characters in which it is written. And it is written in mathematical language. And the letters are triangles, circles, and other geometric figures, without which means it is humanly impossible to comprehend a single word. So we've understood the way our universe is put together by understanding the symmetrical language in which it is written. But it's not just us scientists that are interested in symmetry. Artists, too, have found a fascination with the world of symmetry. Two poets talking about the role of symmetry in the human mind. Pushkin once wrote, "Symmetry is a characteristic of the human mind." And Paul Valéry, a French poet, once wrote, "The universe is built on a plan, the profound symmetry of which is somehow present in the inner structure of our intellect." And it's interesting, it was two poets writing about the importance of symmetry, because I would say of the literary forms, poetry is the one that enjoys playing with pattern and rhythm and symmetry. But not all artists find symmetry such a comfortable concept. I think some artists will say that they find it too constricting, too restraining, somehow not allowing the freedom that an artist likes. If you read Thomas Mann in The Magic Mountain, late on in the novel, the character goes out into a snowstorm on the mountain, almost dies in the snowstorm, and he watches these snowflakes land on his arm, and he sees these, perfect six-pointed stars. And he says about these perfect snowflakes, he shuddered at its perfect precision, found it deathly, the very marrow of death. So I think some artists just find it too deathly, somehow too static, too still. But actually, we mathematicians, we've come up with a language to understand symmetry, and it's far from deathly, far from still. In fact, for a mathematician, symmetry is very much about movement and action. And it's one of my heroes, Évariste Galois, a French revolutionary at the beginning of the 19th century, died at the age of 20 in a duel over love and politics. But already by the age of 20, he'd come up with a language to understand the world of symmetry. And the language that he produced actually shows that symmetry has a lot of movement in it. One of my favorite places in the world, if I was going to be banished and I had to live my life in one place, actually I might choose here the Academy in Marvão because it is extraordinary, but I'll put that second place to the Alhambra in Granada. And one of the reasons I love coming to Portugal is because of all the tiles you see here. But the Alhambra, some of you may have been to the Alhambra, the wonderful walls covered in these symmetrical designs. But actually reading the walls in the Alhambra is quite tricky. Some of the designs don't necessarily look symmetrical. And the way to sort of understand the symmetry is to use Galois' language. He says symmetry in a wall is the way that you can take the tiles, pick them up, move them in some way, and then put them back down again, and the tiles look like they did before you moved them. So for me as a mathematician, it's all about what are the moves that I can make to a shape that mean that when I place it back down again, it looks like it did before I moved it. So for me, symmetry has a lot of movement in it. And so it's interesting that if you look at the one art form that truly does celebrate a connection between symmetry, mathematics, it is probably music. And music, I think, is a place where you see symmetry used a lot in this very active way. And we're going to take an exploration. I've been here this week, as Christoph said, working with these amazing musicians, exploring some of the ideas of connections between mathematics and music. And I'm going to start in the past with perhaps the number one favorite composer for a mathematician, Bach, of course. As Mitzler said, Mitzler was a contemporary of Bach. Bach's music is the process of sounding mathematics. And if I was banished to the Alhambra, that's where I would choose to go as a lover of symmetry. And if I had to listen to one piece of music for the rest of my life, I think I would probably choose the Goldberg variations. And the Goldberg variations for me are a real song to symmetry. So I'd like to welcome Nicolás Margarit, who's going to help us explore a little bit of the mathematics and symmetry behind these wonderful piece of music by Bach. So a round of applause for Nicolás. Thank you. We were very privileged last night that Nicolás gave us a complete performance of the Goldberg variations, and we won't be able to do that tonight, I'm afraid. We're going to give you a little taster to hopefully give you a little feel for the kind of mathematical journey in this wonderful piece of music. So the Goldberg variations, it's 32 movements, and it starts with an aria, the opening movement. And then you get 30 variations, taking this theme from the bass line of the aria, developing it in extraordinary ways. And then after the 30 variations, what's interesting is that Bach comes back to the beginning again, and you hear the aria again at the end of the piece. So for me already, there's an interesting sense of a circle emerging in the Goldberg variations, that you begin and end with the same piece. So I thought we should begin our journey round this circular structure of the Goldberg variations with that aria. And so begins our journey through the Goldberg variations. And as if to accentuate this sense of a circle, when you reach the halfway point, the 16th variation, Bach interestingly calls this an overture. Now, an overture is usually the beginning of an opera or a piece. So it's always saying, where is the beginning of this piece? It's a circle. Where's the beginning of a circle? So that halfway point is almost accentuating the idea of a circular structure that Bach is producing. But there's another interesting circle that begins to emerge if you look at the variations. And somehow for me, the backbone, the skeleton of these variations are the set of canons. Every third variation, as you go through the Goldberg variations, is an example of something called a canon. Now, you may remember canons from school where half the class starts singing, and then a little bit later, the second half of the class sings the same thing, but a little bit delayed in time. So this is the trick that Bach plays in every third variation. So let's hear a little example of that. Nicolás is going to play, first of all, the third variation, the first canon. We hear the first voice coming in, but a little bit later, you will hear the second voice coming in, but it'll be an exact copy of what you've just heard, but just delayed in time. Perhaps you could give us that example. So it's a little bit like those tiles in the Alhambra somehow. You've got the first tile, and then you repeat the tile next to it, one step along, but instead of repeated in space, we're hearing it repeated in time. And so these canons were things that Bach loved playing with. So let's hear that first canon, the third variation, the two voices, the tiles across the wall. So hopefully you heard that pattern being repeated. You heard it the first time, and then a little bit later repeated again. But when Bach comes to the second canon, the sixth variation, he's not just happy to repeat the second voice. He wants to do something interesting, take you on this journey. So what does he do? He says, okay, well, why don't we take the second voice and not have a repeat, but get the second voice to go one note higher. So now it's as if the tile starts here, he moves it along but pushes it up a little bit. So we hear the first voice, but when the second voice comes in, it's a little bit higher in pitch. So perhaps, Nicolás, you could give us that example. So we're going to start climbing as we go through the canons as the pitch of the second voice gets higher and higher. So let's start our climb up this canon ladder. So as each new canon arrives, that second voice is getting higher and higher. But something rather magical happens when we get to the 24th variation, because that's the 8th canon. And if you take 8 steps up through a major scale, you get to the octave. And so actually we sort of return to the beginning again, because the voice almost sounds like a copy of what you've just heard. So the first voice comes in, but when we hear the second voice, it's almost the same, but just an octave. Well, in this case, actually an octave lower. He takes it, sometimes he likes reflecting things down. So here's this structure of a circle kind of emerging, because as Bach has taken the canons up step by step, suddenly at some point we reach the beginning again. And for me, I start to see a structure of a mathematical shape actually hiding inside the Goldberg variations. A circle, yes, you know about a circle, but we've got also this second circle going on inside here. And so actually a circle's worth of circles is something we mathematicians call a torus, or you might know as a bagel or a donut, one of Homer Simpson's donuts. So there's this kind of shape, one circle, but another circle at work again. So let's start to complete this second circle. We'll hear the 24th variation, where we somehow arrive at this moment where the octaves join the thing up again. We haven't finished the piece yet. Actually, there are still some more variations there, and a third canon after the 24th, so the 27th variation. Bach says, well, we can keep climbing this ladder. Actually, so the 27th variation, the 9th canon, the second voice starts an octave and a note higher. And Bach gives this idea, well, actually, this thing could go to infinity. It just could keep on climbing. So perhaps there's almost a structure, maybe not of a circle, but of a spiral, just going up, up, and up. Well, also, symmetry is used a lot, so we've seen this kind of symmetrical shape emerging, but it's also used to do the variations. So this is a trick used by many composers. They will take a theme, and then they might reflect it upside down and play the thing in reverse. And so we see this used a lot in the Goldberg variations. So if we take, for example, the 12th variation, there we hear the first voice, it goes down and then up, and then down and then up again. But the second voice does completely the opposite. It goes up, and then cascades down. Perhaps, Nicolás, you could play us those two little motifs, and you'll hear that the second one is reflected horizontally, upside down, version of the first. So composers love this idea of using symmetry to make something different, new, but related to what you've just seen. So it's just like those tiles in the Alhambra, where they just kind of spin the tile or reflect it. And this is something that's used all the way into the 20th century. Schoenberg is using the same sort of tricks to do his 12-tone kind of music as well. So these are all over the Goldberg variations, these symmetrical tricks at work. So let's hear the symmetry in that 12th variation, the 4th canon. The other place where Bach uses some interesting kind of mathematical ideas is in the rhythm structure of these canons. Because, for example, in the 24th variation, where we heard the octave, that was a piece that had 3 beats in the bar, and each beat Bach had decided to break it up into triplets. So we've got 3 lots of 3s. And Bach, the mathematician in Bach, says, oh, what other possibilities are there? And almost like a combination lock, if you have a combination lock on your bike and you forget the number and you have to go through all the different possibilities and you try and do it systematically, well, this is a bit like Bach has just 2 triangles. On one triangle is controlling the number of beats in the bar, so maybe 2 beats or 3 beats like in the Variation 24, or 4 beats. But how is that beat broken up? It could be broken up into quavers, triplets, or semiquavers. So he's got 2 triangles at work controlling the different ways that you can do the rhythms in these canons. So Bach, the mathematician, makes sure that every single canon hits one of the possibilities of this little combination lock with 2 triangles on. So the 24th variation, yes, that's 3 and 3. But if you go, for example, to the 15th variation, the 5th canon, there we see the bar broken up into 2s, but each beat is now semiquavers. So there are 9 canons all the way to that one, the 27th. 9 possibilities for this combination lock. Bach, the mathematician, makes sure that each one of them is used somewhere in the piece. So a huge amount of mathematics hiding inside this piece. And actually, Nicolás and I have had a lot of fun this week discussing other things that are hiding inside there. There's a kind of strange fractal structure as well, because if you think there are 32 movements, and actually each variation is very often 32 bars. So it's almost like a symmetry in scale, where the whole thing, if you shrink it down, you get a little microcosm of the whole thing. Bach's other obsession was a bit about numerology, and he had actually, we're in the middle of the Euros at the moment. I'm looking forward to England-Ukraine. Our string quartet has 2 Ukrainian players in it. We're going to have a fun evening, I think. But Bach used to have a kind of like shirt number that he played in. So B-A-C-H, if you translate it into letters, 2, 1, 3, 8, added up, it's 14. This was Bach's signature number. And Nicolás has explained to me there's lots of 14s actually hiding inside the Goldberg variations as well. 14 pieces which are in 3/4 time, interestingly, split halfway across the 2. So a huge amount of mathematics hiding here. To such an extent that, really by the time you get to the 30th variation, surely you know exactly what's going to happen. Oh, it's divisible by 3, so that should be a canon. We know where the second voice is going to climb up. But no, Bach plays a little trick on us, and this is called a quadlibet, a musical joke. Has nothing to do with the structure of the piece up to that point almost. It's just a play on 2 folk tunes of the day. But I think that's very typical, actually, of artists. What they love doing is setting up expectations of symmetry, and then they like to break that expectation. And I have a colleague that I work with in Japan, Professor Kurokawa, and he took me on a trip up to kind of the Alhambra of Japan, Nikko, with the beautiful Shinto shrines and Buddhist temples. And I remember we took this picture in front of a great gateway, and then we walked up the gateway, and there are 8 columns with this beautiful symmetrical design down the columns, except that one of the columns is upside down. And I said to Professor Kurokawa, wow, the architect must have been so angry with the builder for getting this one the wrong way round. And he said, no, that was a very deliberate act. And he referred me to this wonderful thing called the Japanese Essays in Idleness from the 14th century. The Japanese Essays in Idleness, the essayist wrote, in everything, uniformity is undesirable. Leaving something incomplete makes it interesting. It gives one the feeling there is room for growth. So the quadlibet is almost hinting at that upside-down column. You don't want symmetry everywhere. Something a little imperfection is always somehow intriguing. So let's end our journey through the Goldberg variations with a quadlibet. Big thank you to Nicolás. Thank you. Was actually a member of an interesting society that was formed by his contemporary Mitzler. It was the Corresponding Society for the Musical Sciences. And intriguingly, Bach insisted on being the 14th member to join the society. Actually, I think, in a way, the Academy in Marvão has got a similar spirit to it, that it's wanting to look at connections between music and art, and also science. And I too have helped form a new centre at the Royal Northern College in Music in Manchester, in collaboration with Oxford University. Our organisation is called PRISM. It stands for Practice and Research in Science and Music. Seemed a perfect acronym, PRISM. And I've been working there with a very interesting composer when we formed this. And in a way, this residency is, we hope, a beginning of a twinning between our two organizations here in Marvão and in RNCM. And I've been working with Emily Howard, looking at kind of modern connections between mathematics and music. Because I've always felt many people have talked about connections between mathematics and music, right back to Pythagoras. After all, the notes that we play on the piano somehow have a very mathematical foundations. Rhythm as well, very mathematical. But that feels like the vocabulary and grammar of music. But what are the big stories that you can tell? And for me, in mathematics, the really important things are the proofs that we write, the stories that we tell about the numbers and geometry. And they're somehow the really important things, the stories that we tell. And I've always felt, actually, they have a very musical quality to them. The idea of a mathematical proof, starting kind of from the axioms, the known things, and then taking you on a kind of logical journey to somewhere new. I felt maybe that's why I love music, because I feel there's this connection. So I was intrigued to share this with Emily Howard to see whether she felt that the proofs that I do they have anything in connection with the music that she composes? So we're going to take an exploration through a piece that we collaborated on with a string quartet called Four Musical Proofs and a Conjecture. But if we're going to set off on our journey, we need the axioms. What are the axioms for the string quartet? Well, it's probably the first string quartet. The first string quartet by Haydn, the father of the modern string quartet. So I'd like you to welcome the Mendelssohn Quartet, who are going to play the first movement of the first ever string quartet, and then I'll take you on a journey of mathematical and musical proof. So please welcome the Mendelssohn Quartet. whole quartet. So I offered Emily Howard a kind of challenge. I said, well, why don't I show you some of the proofs that I love as a mathematician, different styles of proof, and see how you would respond to those as a composer. And what I decided was to go right back to where proof started, which is with the ancient Greeks. Euclid's Elements is somehow the place where we began writing our kind of mathematical stories or mathematical compositions. So I took several different styles of proof and offered them up to Emily. One of the first I offered was something we call proof by contradiction. One of the things the ancient Greeks discovered, that a number, the square root of 2, a number which when you square it gives you 2, well, is there a fraction, for example, that might be, you could square that and you get to 2? And it turns out there isn't. You can't find a fraction. But how do you prove that there is no fraction whose square is 2? The ancient Greeks came up with this clever idea. They said, suppose there is. Suppose the opposite is true. Suppose there is a fraction. And what they then did was to follow the logical consequences of that assumption until suddenly they reached a contradiction, which showed that their assumption at the beginning must be false, and therefore there can't be a fraction whose square is 2. So I explained this proof to Emily, and she said, oh, that's interesting. Okay, so in some ways, the Haydn, we're going to take that as the axiom of the string quartet. So let's take the opening bars of the Haydn. Perhaps we could hear the opening bars of the Haydn again. The final bars of the Haydn. So how are we going to get there? Let's hear the final bars. This is where we're trying to end up. Now, you've already heard how Haydn solved that, a very natural way to get from the beginning to the end. But Emily thought, well, what if we try a proof by musical contradiction? How could we find a way to get from that opening bar to the end by contradiction? So she said, okay, I'm going to take that opening first bars and take the opposite of that, and then follow the musical conclusion of what the opposite of those opening bars might be until I get to some sort of musical contradiction. So first of all, thinking about what's the musical opposite of something. That Haydn, all the four players very together, a forte, then a piano, very fixed tempo. So Emily just took the complete opposite of that, where the thing is accelerating all the way through the piece, very, very dynamics, very sort of slip-slidey playing. And actually, as this builds, the quartet it's harder and harder to play until suddenly the quartet just blows up and reaches a contradiction. So let's hear the first musical proof by contradiction. So by assuming the opposite of the Haydn and taking that to its logical conclusion, somehow the quartet are expected to accelerate more and more until they just can't do it, and we reach our contradiction, which somehow proves that the final bars are true. Well, the second sort of proof I showed to Emily was a more geometric proof, that Euclid's elements are full of beautiful proofs of how to make geometric shapes like pentagons and hexagons. But what they do is to take very simple ingredients, and by putting these simple ingredients together in step after step, you can suddenly make these amazing shapes. The only shapes you're allowed are a straight line and a circle. But with those, you can build a pentagon or a hexagon, and the architects in medieval time would use just these ingredients to make the shapes that you see in a cathedral. So I showed this idea to Emily, and she said, oh, that's interesting. Okay, so I'm only allowed very simple moves to get from one bit to the next, and I have to make something sort of complex out of my beginning ingredients. So she actually asked the quartets that we first performed this with in the UK, the Piatti quartet, what were their favourite pieces of music. And one of the pieces they mentioned was one of the late Beethoven quartets, 130. And so Emily took the scherzo of that and a little motif in the scherzo, and the challenge of could she, by very simple steps, get from that Haydn that we just heard to the Beethoven. So let's hear the Haydn again. This is where we're starting, just that little opening snippet. But where we're going to try and end up is this little bit of Beethoven. Okay, but we have to make nice, simple, logical moves on the way. So Emily said, well, what are the sort of versions of a line or a circle? If you heard in the Haydn, the four are playing very equally, but by the time we get to the Beethoven, it's really the first violin that's sitting on top of a little accompaniment. So we've got to somehow soften the lower half of the quartet. So let's just hear the first move that Emily makes, which is to somehow halve the lower half of the quartet. So we've started to lose some notes. Very simple step. So let's hear the whole of the geometric proof, the second movement of this, and see if you can spot what's the simple thing that's been done each time which moves us to the next bit. And Emily chose, being a true mathematician, 11 moves, a prime number. In 11 moves, we're going to get to Haydn to Beethoven. So the third sort of proof I showed to Emily was an important style of proof called proof by induction. This is a trick we use a lot. For example, if we have a formula and we have to show that this formula works for every single number that I might put in there. But the trouble is we have infinitely many numbers, so I can't check for every number. So we've come up with this cunning technique called proof by induction. Actually, it's the principle I use to climb a ladder. I'm terrified of heights. And so the way I climb a very tall ladder is saying, okay, first of all, it's quite simple to get on the bottom rung of the ladder. That's not too difficult. I'm not frightened of doing that. Okay, I'm on the ladder. And then, the proof by induction to get up the ladder. So, suppose I'm in the middle of the ladder. Well, it's not too difficult to just go one more rung up. I just have to work out how to get onto the next rung. So this is the principle of proof by induction. You show the first how to get onto the ladder, and then you show the formula kind of works. If I've got to this far, that I just need to go one step further and show why I can get to the next step. So Emily thought, oh, that's very interesting, because the Beethoven, if you know the Beethoven, and you'll hear it a little bit later on, that little motif that we've arrived at with the geometric proof, actually Beethoven uses it again and again and climbs in pitch as if he's climbing a ladder. So it seemed perfect to try and prove, in a way, how can we get from just a simple ingredient to show why we can take the Beethoven as far as we want up this ladder. So what we need to do is we need to start with kind of what we're trying to prove. So perhaps we could start with just the example of the little Beethoven again. So we need to get on the ladder because we want to show that this is true for every single pitch somehow. So we need to start at the bottom of the ladder, which is the bottom of the quartet, which is the cello. So our first step in this proof is to put that little motif down in the cello. And now we have to assume, okay, I've got a certain point on the ladder, I've got some sort of pitch, but I need to prove why I can climb to the next ladder, rung on the ladder. So, and often what this involves is a little bit of slippery algebra to sort of maneuver the formula. In fact, I spent a wonderful week. I think these musicians thought they were coming to do some music, but we've actually done a lot of mathematics. They've been doing some proofs with me. We did some proof by induction, and they saw this kind of slippery nature of the way you get to the next rung on the ladder. And so what Emily did was to take the motif, and if you've got to climb a bit higher, maybe you've got to do a little strange movement to get there. So let's just hear just one of the steps, how we're going to get from one rung of the ladder to the next. So there was that little bit of algebra, got us to the next step. So now let's put this all together, the proof by induction, to show why Beethoven can climb up his little musical ladder. All the way to infinity. So Beethoven stops at some point, but as you can hear, the proof can go all the way off to infinity. So the fourth sort of proof I showed Emily was one I love in mathematics, which is somehow algebraic transformation, which can take you from one area of the mathematical landscape to a completely, seemingly unrelated area. One of my favorite proofs that I read actually when I was an undergraduate at Oxford was a proof by Pierre de Fermat. Some of you may have heard, a very famous French mathematician, 17th century. He showed something rather extraordinary. A prime number, an indivisible number, if you divide it by 4 and it has remainder 1, so something like 41, when I divide it by 4, that has remainder 1, Fermat proved with an amazing logical argument why you could always write that as 2 square numbers added together. So in this case, 41 is 5 squared plus 4 squared, 25 plus 16. Now, it seems, when I read this, bizarre. How can you show that primes that have 1 on division by 4 can be written as square numbers? But Fermat takes you on this extraordinary journey and shows you how they're 2 sides almost of the same equation. So I offered this to Emily, and she thought, okay, what's that, a musical version of that for me? So she thought of the idea of, yeah, well, I've got to get from one sort of music to the other. And she asked the Piatti Quartet, another of their favorite pieces, turned out to be Schubert's Death and the Maiden, also a favorite of the Mendelssohn Quartet here, I think a favorite of many people. So Emily took that challenge of how can I get from that little motif that we've heard from the Beethoven all the way to the opening of the second movement of the Schubert. So let's hear the proof by algebraic transformation to get us from one quartet to a completely different quartet. The lifeblood, actually, for a mathematician are not the things that we know, the things that we've proved already. Actually, are the things we don't know, things we call conjectures. That's what gets me up in the morning to do my mathematics, not the things from the past, but the things, hopefully, of the future. For example, we just heard the Goldberg variations, a part of them, but we have something called the Gold-Bach conjecture, which is that every even number can be written as two prime numbers together. But we don't know if that's true. Maybe there is an even number which can't be. That is still to be proved. And I think for composers as well, they love the music of the past, but they want to compose the music of the future. And very often what you need to do in order to be able to solve this new problem is to come up with a new bit of mathematics. For example, one of the great discoveries which opened up many mathematical conjectures was the discovery of imaginary numbers, the square root of -1. So what about coming up with new sort of ideas in music to be able to perhaps make breakthroughs? Now, on the piano, you're stuck with the notes that you play here, and string players will learn to play a chromatic scale, for example, which are the notes here. Eva, perhaps you could play us a chromatic scale. This is what many students will learn. But what about if we put some notes in between those? Notes that we can't play on the piano, but the violin can play. Certain things called quarter tones. So perhaps you could give us a quarter tone scale. So perhaps we need to make a new discovery of some music in order to be able to make some sort of progress. But how would you discover those quarter tones? So Emily had this interesting idea that one of the things that string players do is vibrato. So let's perhaps hear the first 4 bars of that Schubert without any vibrato at all. But often they like to make it a little bit warmer by putting some vibrato on it. So perhaps we'll do a molto vibrato on the first 4 bars. But what if you push that to the absolute extreme and did a incredibly wide vibrato? Maybe you would discover by wobbling either side new notes like the quarter tones. So let's hear it like kind of an incredibly exaggerated vibrato. So in the musical conjecture, the 5th movement, what Emily does is to use this very wide vibrato to discover these new notes, kind of the imaginary numbers, these quarter tones, in order to create perhaps a new sort of music, which we're not quite sure by the end where it's going. and off into the unknown. So a big thank you to the Mendelssohn Quartet for taking us through Emily Howard's 4 musical proofs and a conjecture. Thank you. And since our proof did get us to that Schubert Death and the Maiden, we thought we would finish the quartet rewarding them with playing one of their favourites, the second movement of Schubert's Death and the Maiden. So a big thank you to the Mendelssohn Quartet. What an amazing piece of music. Well, the Meister singers used to use a technique which they called a bridge between two different bits of their kind of singing. And so we thought we would use a kind of a conversational bridge to take us to the next part of our presentation. Nuno, Maulide and I are going to have a little conversation about our passions of science and music before I'll hand over the stage to him. So perhaps I can welcome Nuno to the stage. So welcome. I sort of gave some hint of how I thought, like, musical proof, the things that I spend my time piecing together, kind of had a musical resonance for me. What about your scientific research as a chemist? Very different from mine as a mathematician. You get your hands dirty a bit. So, but, does it have any resonance for you as the music that you play? Or?
Absolutely. So one of the main aspects of our research is devoted to making molecules with a specific purpose. Something that could be a pharmaceutical, a new cosmetic, a new fragrance, a new aroma. And we sometimes devise a synthetic route, how to get from starting materials, something you can buy, all the way to that substance. And it becomes a kind of an obsession, right? You try very hard to go from A to Z. It's not a linear path. There's a lot of twists and turns. And at the very end, when you finally succeed, every one of these molecules becomes associated to a piece that I learned at the piano. So very much in the same way as we fight hurdle through hurdle to get to the target molecule, so I also fight hurdle through hurdle where I'm learning the bits and pieces, the nooks and crannies of a new piece of music.
I suppose, you know, you are aiming for some final target, a bit like we were talking with, you know, getting from Beethoven to Schubert, but you've got to make sure that each of the things that you do in the lab make some sort of sense, is natural, but hopefully you end up somewhere new. Very intriguing.
And what's very interesting is, like many things in life, although we scientists tend to focus very much at the final goal, a lot more interesting is the path.
It's the journey.
It's the journey to
Absolutely.
Get there. And the same thing happens in music, right?
Yeah, you don't want just the final chord, you know, exactly. That would be boring. But
it's the whole route that you take to get there that really...
Yeah, there's a very famous Fermat's last theorem, which took us 350 years to prove. Actually, what it states is not that particularly interesting about an equation, but the journey it took us on and the places we had to go, that's what we enjoy about reading about it. Do you listen to music in your lab? I mean, is that something, or when you're kind of coming up with new ideas, is going to the piano an important part of doing your science?
Yes, because it's, and it's very interesting that we tend to dissociate, and I'll tell more about that in my presentation, we tend to dissociate artistic endeavors from scientific pursuits. Although the physicists, the mathematicians, the chemists that come up with solutions to very, very tricky problems of our world are using the same very creative principles that musicians, artists, painters use as they are creating works of art.
And I think this is one of the tragedies of our education system, certainly in the UK. I don't know whether you find this, but at the moment the creative arts are really being hit hard, and many scientists have said, well, if it wasn't for the music I did, or the painting, or the poetry, I probably wouldn't make the discoveries. So it seems very short-sighted of government to do that. I mean, are you finding that in Austria or here in Portugal?
So as a Portuguese who no longer lives in Portugal, I do accompany what goes on in the country with a lot of interest, and it's indeed very stressful or distressing to see and to witness how the performing arts seem to be neglected when actually they lend such an important role to what we as a species, as human beings, have to do on this planet. Austria, of course, is a little bit more, I mean, Austria is the country of music, right? And so they're a little bit more careful. One of them. And they are certainly very, very much devoted to making sure that even through a pandemic and difficult times, that the musicians, the performing artists, are supported appropriately.
Wow, that's fantastic. And it's so exciting. I mean, I've had an amazing week at this academy, you know, sharing my mathematical ideas with musicians, hearing them come up with stimulating things. And I think that's the interesting challenge. You know, there are a lot of science art projects, but I think for us as scientists, the challenge often is, can the musicians offer us something new, a new insight? I mean, have you ever had an experience which really emerged out of, say, a musical question that led to a scientific discovery?
So certainly a lot of Bach's music, because of its structure and order, is ideally poised to allow you to crack problems, because I think you activate the same part of your brain as you are tackling something difficult at the piano or at the violin, as you do when you are faced with a complex problem in mathematics or in physics or in chemistry.
I think that's so right. I think that's why I listen to a lot of music, or I'll sometimes, I play the trumpet and I've been trying to learn the cello, and I will often go to that when I'm having, I've got nowhere with the maths, and somehow just massaging my brain with music means that when I come back to the desk, it's somewhere, I think I know what to do next.
And some of these problems have a way, when they pursue you for weeks, months, and years, they have a way of lodging themselves in your subconscious.
Yes.
To the point where you're actually better off removing it from your day-to-day preoccupations and just let your subconscious do its magic.
Yes.
Very often you go to sleep with something unclear in your mind, and then you wake up.
Yeah, this is my justification for not being at my desk very often. That I'll go off and listen to a concert, or I know I'm doing some work. But
I guess our partners are the ones who suffer a little bit more with that. They sleep next to us and listen to us mumbling, probably with our subconscious working through those problems. And then in the morning, 5 a.m., you wake up and you jump out of bed.
Eureka!
Eureka! And
out of the bath.
Get back to sleep.
I think this is a really exciting opportunity here at Marvão to explore new ideas of connections between music, art and science. If you were going to pitch a project to them that you would love to explore this dialogue, what would it be? See if we can tempt them.
So I think there would be quite a few different ideas. I can think of molecular gastronomy, so something which has to do with food, cuisine and chemistry.
I like the idea.
And yet, I think we have not yet explored the dimension of food as it ranges to music. And so we could have a kind of a circle.
Well, we have been doing a lot of food this week. It's true, actually. Amazing food here. So I like that idea. Let's pitch that to Marvão Academy.
Another one would be, I think there's a lot of intrinsic beauty in chemistry and in chemical experiments. And I think there should be a way to merge certain spectacular chemical experiments. I could come here in the middle of this room and make something blow up or create something luminescent out of two colorless liquids. And I think that type of emotional response that one gets as one sees such a moment, you cannot sit and see something go up in flames without having some kind of very visceral emotional response to it. And it's exactly the type of emotional response that you also have when you, for example, listen to parts of Schubert's Death and the Maiden, as played by this wonderful quartet.
I'm looking forward to some gastronomy and chemical explosions here in Marvão. But I'm going to leave the stage to you for the final part of our afternoon and evening. Nuno is going to give us a presentation with demonstrations of the piano, I think called Chemistry and Creativity. Is that right? Right. But I'm going to take my leave, so thank you very much for all your time.
In Portuguese before we go on. É prazer e uma honra estar aqui na Academia de Música, Arte e Ciência em Marvão. Primeiro porque, como português, eu não fazia a mínima ideia de que a iniciativa existisse e não tinha nem sequer noção do valor que há em juntar a música, a arte, a ciência, porque, na verdade, como eu espero poder mostrar na apresentação que vos vou mostrar daqui a alguns minutos, não são coisas assim tão diferentes. And so going back to English, this first picture, which is probably visible to you following us remotely, is a painting by a famous American artist called Clary Meserve, and the painting is called Einstein's Art and Science, which I think is a very fitting image to illustrate indeed what I plan to tell you about today, namely about art and science. And you may wonder, what is an organic chemist doing, coming here and telling us about art and science, since we as a society have a lot of prejudice considering that art and science are usually more two opposite poles of human activity. We typically go more art versus science. We typically try to look at budgets of countries and figure out, well, do we give money to arts or do we give money to science? After all, art is driven by emotions, by feelings. A painter dreams of something, a musician experiences intense pain and creates a painting, a work of music. Whereas science is driven by data, by facts, by hard, cold, analytically interpretable facts. I'm not talking about alternative facts, which have become quite a thing in our society since the Donald Trump era, because actually, if you think about it, alternative facts are nothing else but a very narrow-minded interpretation of certain facts in the way that best suits your emotional predisposition. So in a sense, alternative facts are a bit of art in the world of science. We have also seen these wonderful musicians which have been here in this week in this academy, and we have seen that they have very, very strong and expressive personalities. After all, artists are a bit eccentric people. They are very expressive, very emotionally connected individuals, whereas we scientists are what you would call, I write it on this slide, technical introverts. It's kind of an euphemism for geeks or nerds, right? That's what a scientist should be. And yet, ladies and gentlemen, I would like to convince you that there is a lot more in art and science than what meets the eye. And that much more has to do with the fact that art and science both seek answers to questions that are deep, deep down at the essence of what it means to be a human being. They both search for science for answers to questions such as, what is true? What is true in this world? How does our world function? How does this universe work? How can we make society move forward? I mean, science tries to do that in a very obvious way by creating new gadgets, new toys, new things that allow us to live a better life. I write better between quotation marks. Sometimes it's better, sometimes it's not that better. But at least that's the way science tries to move society forward. Art does exactly the same. Art tries to bring us more and more in touch with who we really are, with this flesh and blood and bones that makes us human beings. And I think at the intersection of science and art, you often have a moment of wonder. And that's because science and art are both very open-minded in how they look at the world. When done at their very best, they take no prejudice, they take no special preconceived notions, they look at the world around us in an open, unbiased way. And working at the University of Vienna, it would be very fair for me not to mention a gentleman called Theodor Billroth. Mr. Billroth was a famous physician, medical doctor, working at the General Hospital in Vienna, the Allgemeines Krankenhaus, which was at its time in the 19th century the very best center for medicine in the entire world. And Mr. Billroth was a pioneer in gastric surgery. He devised two procedures, Billroth 1 and Billroth 2. If you are a medical doctor listening to this, you will recognize those procedures as you learn them during your medical studies. It's still taught and still practiced to this day. So what he done is amazing from a medical point of view. Little do we know that Mr. Billroth was a very talented pianist and violin player, to the point that he really hesitated whether he should pursue music or medicine as a career. I guess the medical doctors all over the world are very happy that he chose medicine. We can be happy that his musical side inspired him to, for example, befriend a certain Johannes Brahms as he was living in Vienna, to the point that Brahms would send copies of his manuscripts before publication to Billroth, asking him for feedback on the musical quality. And Billroth himself wrote two dissertation theses at the end of his studies, one on gastric surgery, the other one on a scientific analysis of musicality, where he tries very scientifically, very systematically to categorize and qualify what does it mean to be musical. We just heard 4+1 young musicians who we would immediately instinctively say these are extremely musical individuals. But what does that really mean? Billroth wrote a scientific analysis of musicality and then wrote in one letter, it is one of the superficialities of our time to see in science and in art two opposites. Imagination is the mother of both. And indeed, I think there is the connect between art and science that comes precisely at the level, as we just discussed with Marcus, of what processes go on in our brain as we are engaged in each of these two types of activities. At the end of the day, science and art are all about communication and creativity. You know, I like to say that our world, as we know it, exists in two very opposite dimensions, an abstract dimension. These are things we cannot really see, right? Our emotions, our thoughts, they are there, but you can't have them in your hands, you can't put them in a bottle. And then there's a very concrete dimension of our world, the shirt I'm wearing, the chair in which you are sitting, the microphone which is transmitting this voice to all of you listening to us remotely. These are very concrete things of our world. And I think art and science make the bridge between the abstract and the concrete. They just do it in opposite directions. After all, art takes abstract emotions, feelings, sensations, and creates concrete pieces of art. Science does the opposite. It takes concrete observations from our everyday life, the fact that the sky is blue, the fact that the sun is shining, and devises abstract theories to explain those observations. For example, in this slide, for those of you who can see it, there is a very nice picture of a fruit. It's actually a half orange. And I think when you look at an orange, in your brain, there is a smell memory, there is a taste that is evoked, there is even a tactile sensation when you have an orange in your hand. These are all very concrete and palpable things. And then we, organic chemists, associate all of those, especially the smell and the taste, with an abstraction, namely a molecule, D-limonene, the main component of essential orange oil. And so at the end of the day, I think we can all agree that science and art are nothing else but two different ways of looking at nature, two different depictions of the natural world around us. And that brings me to the first piece I would like to share with you today, an impromptu by Franz Schubert. We just heard beautiful music by Schubert in G-flat major. And I think whenever you hear these things, and you're not necessarily a professional musician or someone who has studied music, you might wonder why on earth would Schubert and all these composers write pieces in D sharp minor, G flat major? Why don't they just write everything on C major? It would anyway sound the same. And in this particular case, G flat major is an extremely tricky thing because it places all the music on the black keys at the piano. And so the publisher of Schubert said, Franz, I think this is not going to be a popular piece. Why don't we publish a version of this piece in G major, which is almost all on the white keys. There's just one black key, the F sharp, and it would be much easier for people to play, therefore a much bigger success, commercially speaking. And Schubert said, no, it won't sound the same way. Why don't you listen to the beginning of this piece in G major? Listen to the G flat major, the same thing. I think you don't need a degree in music to recognize that while G major is open, luminous, sunny, happy, G flat major is introspective, it's personal, it's intimate, it's dark. No wonder Schubert chose G flat major. He wanted this piece to be personal and somewhat dark and intimate, because when he wants to make the music luminous and full of light, he does. B major is a lot more luminous than our G flat major. And although this is something that you feel, I think you all could hear the difference between one and the other, this is also something that you can explain mathematically or scientifically. After all, it turns out that if you take a metal plate and you drop some sand particles on it, of course the sand will be spread in a random way. And then if you take one of the bows, for example, that we have just seen the Mendelssohn Quartet use, and you take that bow and you go on one of the edges of that metal plate and you scrap it against the metal plate, making a little bit of a sound, as you do that sound, the sand particles on the metal plate will spontaneously organize and form a geometric shape. And depending on which point at the plate you play the bow, the geometric shapes will be different. And that's because, of course, the sand particles are reacting to the vibration frequency of the bow and are self-assembling according to that vibration. The same thing happens if you play notes on the piano. I'm going to show something which was published in a paper in Science, showing how different notes played on the piano also result in different patterns of assembly of certain particles around a metal plate. And you can see, looking at that picture, how F sharp, which is the same as G flat, and G look completely different. One of them has particles concentrated in the middle, the other one has particles concentrated at the periphery. No wonder they then sound so different from one another. I hope you enjoy this impromptu by Schubert in this intimate walk through the nature. Imagine you are in Marvão. Maybe Schubert would have enjoyed being in Marvão and walking through the nature here as he plays this piece. Now, as an organic chemist, I do have to tell you a little bit of what I think is organic chemistry. And I think, as I just alluded to in the conversation with Marcus, I feel there is a key word that we organic chemists deal with in our daily work, and that is the word build. We are a little bit like the Lego players of the chemistry world. We spend our days and weeks and months and years trying to find ways to build molecules by taking smaller Lego pieces and bits and assembling them into creating molecules of interest to society. And it's very interesting if you think about the notion that every single day around the world, not even that difficult, an organic chemist creates a molecule that never before existed on the face of this earth. I will let this sink in. I repeat it. Every day, an organic chemist creates a molecule that has never before ever existed on the face of this planet. Isn't that amazing? Every single day, we are engaged with making things that never existed before. That, of course, allows us to construct entirely new things. Actually, the imagination is the limit when it comes to imagining a new chemical structure. And this means we can probe the world around us in very, very new and creative ways, right? After all, what happens when something that was never on this planet is put on the planet? Maybe something interesting, right? Maybe something very creative. And so I like to say that synthetic chemists design chemistry and design chemistry function at the precision level of a single atom, because indeed we can change an atom with a different atom and therefore create a molecule that never before existed. And when we do so, we are very much reminded of the fact that this is not something that one chemist does alone. This is something that a team works on. And I think in mathematics, as in chemistry, as in physics, there is an intrinsic value to collaborative research, right? When more than one different research and researcher fields gets together to generate new scientific knowledge. That is their common goal. And I think there is a very interesting piece that illustrates the value of collaborative research. That's a Chopin etude, because it's, as in most pieces by Chopin, divided in a melody and an accompanying part. But when you listen to the melody, it's not really something that you are very proud of. Repeated notes, 1, 2, 3, 4, 5, 6. How could Chopin think of something as boring as that? Loads of repeated notes, repeat. What's the interest in that melody? And the accompanying part, ladies and gentlemen, it's nothing better, nothing to write home about. Like a rusty old jukebox, a realejo, as you would say in Portuguese. I think you got the message. And yet, when you put this melody, this boring melody, with this uninteresting accompanying part, a touch of the pedal, and it will sound as if water is flowing out of this piano. Illustrating something which is also very typical of scientific research. After all, the perfect example of collaboration is a case where the whole is more than the sum of its constituent parts. That is exactly the same as this piece by Chopin, which I hope you enjoy, and I hope you don't get drowned by all the water that will flow out of this piano. As we proceed in this journey, of course, I should mention that there are not a few examples of scientists who were also musicians, or maybe musicians who were also scientists. A very popular case and a very well-known example is the case of Sir Edward Elgar, actually a very celebrated British composer who was also a very accomplished chemist. Sir Edward Elgar had a laboratory in his backyard where routinely explosions would take place because he experimented a lot with phosphorus, very pyrophoric material, very prone to going kaboom. But he also designed very interesting and useful pieces of equipment, for example, an apparatus to purify H2S, sulfuric gas, which is still used to this day, called the Elgar apparatus for the purification of H2S. A colleague of mine called Elaine Chu, professor in London, has actually also become a kind of a person that embodies this connection between scientists and musicians. Elaine is a very accomplished pianist who seeks to look at the patterns of cardiac rhythm, essentially taking heartbeat patterns, typically on patients with arrhythmia. And then she takes those patterns and combines them into pieces of music to kind of explain how, after all, what we do when we interpret a piece of music, that is not to play it pack, 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 but to allow what musicians call a little bit of rubato, that is to say some bending and distorting of time, is exactly the same thing that happens in patients which have cardiac insufficiency, as their heartbeat becomes a little bit less regular and accelerates a little bit and then slows down every now and then. I think for us chemists, probably the very best example is that of Alexander Borodin. Mr. Borodin, a very accomplished musician, but also a hell of a chemist. Mr. Borodin, for example, developed two transformations, one of which I teach every semester in organic chemistry 2 at the University of Vienna, the so-called Borodin reaction, a reaction in which a silver carboxylate is converted into an alkyl bromide. He was also the first person to observe a reaction which at the time was very exotic, namely the dimerization of an aldehyde to give a second compound, which we now know as the aldol reaction, one of the most celebrated reactions in organic chemistry. And as we have already seen in the presentation of Marcus, clearly there is a hidden scientist in the history of music, Johann Sebastian Bach, right? And I think the piece I would like to play for you from Bach, Choral, is a very good illustrator not only of his ability as a hidden scientist, but also of fashions in science. And that's because this is from the time when Bach was Kapellmeister in Leipzig. It was his final position where he died eventually. And as a part of his role in Leipzig, he had, as a cantor of the Thomaskirche, he had as a job to compose the music to accompany the religious service. And so what Bach had to work with was a congregation of people very eager to sing, but who couldn't sing that much. What did they sing? They sang these typical hymns of the ecclesiastic, one of which was Jesus bleibet meine Freude. You have to imagine, ladies and gentlemen, this was something that in 1700s, whatever, every man in Leipzig or woman could stand up and sing. Jesus bleibet meine Freude, and so on and so forth. And so Bach thought, I have to work with this. How can I work with this? I can harmonize it. Would have been enough for many, many composers, of course not enough for the genius or the mathematical genius. And he thought this sounds a little bit empty, a little bit boring, a little bit slow. Why don't I compose a second melody that will kind of run parallel to this one, fill in the nooks and crannies, fill in the gaps, and make the whole thing sound a little bit more full. You know what the second melody was? This accompanying fill the gaps melody was? Something which many of us even heard in ringtones on smartphones on our day, right? And the combination of the two, although they sound quite different, works like a charm. I find it extremely ironic that the melody which every born young adult could sing by heart without hesitation is now to us essentially an unknown melody. The one that Bach composed as an accompanying to fill in the gaps is now something that we all recognize and smile and rejoice at. And something similar to that happens in science. I could show you a scheme here of a reaction including organomercury compound. Mercury compounds are extremely toxic, they accumulate in the brain. You don't want to work with organomercury compounds ever. Using a stoichiometric amount of palladium, that's a lot of a very precious and again very toxic metal, to achieve some kind of carbon-carbon bond forming process. This was a reaction published by a certain Mr. Richard Hayk in 1968. Completely a useless reaction, nobody paid attention to it. Mr. Hayk actually had to stop his career because there was no funding for this type of research. Fast forward to 2010, and this is one of the reactions that forms the core so-called palladium-catalyzed cross-coupling, a reaction for which a Nobel Prize in Chemistry was awarded in 2010. Iron law of science, what today may seem like all the rage and very, very hype, may be completely forgotten 30 or 40 years from now. What today seems like an exotic, useless endeavor may be the next groundbreaking Nobel Prize discovery in a couple of decades. And I think there's a lot more to Bach's career and life that matches the life and career of a scientist. Because I just told you Bach ended his career, that's a place where he achieved international recognition, in Leipzig. And you may wonder, how does it happen that the musician actually ends up in a position in a certain city, especially in the 1700s, in the 18th century back then. And that was not very different to the way things happen nowadays. So Bach came to Leipzig because the previous holder of the position which he had, the cantor position in Leipzig, a certain Johann Kuhnau, passed away. Mr. Kuhnau died in 1722. The position was vacant. So the city council of Leipzig made an advertisement and invited talented candidates to apply to fill this position. They were overwhelmed because, of course, Leipzig was one of the key centers of music in the German-speaking world back then. And the city council interviewed some of the musicians who they felt were most talented for that position, and they made a short list, just like you do nowadays in the German world when it comes to filling a professor position. You also open an advertisement, people apply. That's how I came to my position in Vienna, right? I sent an application, then I was invited for an interview, and then there was a short list, number 1, number 2, number 3, and then the head of the university goes and negotiates with number 1, and eventually with number 2, and eventually with number 3. And you know what that short list looked like? So those at home will see it projected right now. It's not the short list that you might expect, because you see position number 1 is occupied by Georg Philipp Telemann, position number 2 is occupied by a certain Christoph Graupner, and only position 3 features Johann Sebastian Bach. And how things turned out is very similar to how things turn out in real life nowadays in academic positions. Telemann, probably the most celebrated composer in the German-speaking Baroque of his era, Telemann had a position in Hamburg. And so the city council of Leipzig told him, we want you. He said, okay. He went to Hamburg and he said, Leipzig wants me. What will you offer in exchange? And Hamburg said, we will raise your salary and we will give you a new house. And so Telemann said, wonderful, I will stay in Hamburg. And he told Leipzig, I'm sorry, I cannot accept your offer. The city council of Leipzig, who very disappointed, said, okay, then let's go to number 2, Christoph Graupner. You probably never heard of Christoph Graupner before. If you type his name on Google, you will find a Wikipedia page which says Christoph Graupner best known for being number 2 in the hiring process where Bach was number 3. It is a claim to fame, right? To come above Bach in a short list. Christoph Graupner was also a musician hired in Darmstadt, a very stable position. So he thought, I go to Darmstadt and I say, Leipzig wants me. What can you offer? And Darmstadt offered him a new accommodation, the possibility to hire an assistant, and a raise in salary. And Graupner said, okay, then I will stay in Darmstadt. And then understanding that Leipzig had no choice but to go to number 3, and eventually Mr. Number 3, Johann Sebastian Bach, had not gotten any other job. He had just been kicked out of his previous position and he had no desire to stay there, so he just accepted. This is also what you do nowadays in appointment professorships processes in Central Europe. You always set in number 1 the person you would really like to get, but who you know you probably will not get. And in number 3, whatever you do, you put someone who has no choice but to come, so that you don't fail the appointment at that point. This was Johann Sebastian Bach, to the point that Christoph Graupner, and this is all, you can go to Leipzig in the City Council archives and you will find all this documentation. You will find a letter from Graupner where he declines the offer from Leipzig, and he ends by saying, Bach is a musician just as strong on the organ as he is expert in church works and capelle pieces. He will honestly and properly perform the functions entrusted to him. A kind of a way to say, don't be too sad. The number 3 is not that bad of a scientist, or a musician in this case. And indeed, he was very correct, because Bach would go to Leipzig on the back of this number 3 appointment and excel to become probably the most beloved composer of the Baroque era. Now, a lot of what we do in science is about trying to find patterns, right? I just said we look at concrete observations of the world around us. Sometimes they make no sense to us, sometimes they are very strange, and we try to recognize some kind of pattern out of those things. And the next piece I'd like to play to you is a relatively short prelude by Rachmaninoff, where it's a lot about pattern recognition in what, for example, the right hand does all over the piece. And while this pattern is going on, the left hand has a very haunting and beautiful melody. So I hope you enjoy this little moment of pattern recognition as Rachmaninoff takes us in a journey that goes from explosiveness to very intimate and romantic and melodic treatment. As we come to the end of today's presentation, I want to take you to a different type of composer. Of course, we could not finish without one of my favorite composers, namely Claude Debussy, a Frenchman who wrote music about America, about Southern America, about Africa, without ever having set foot outside of France. He even wrote beautiful Spanish-style music, although he himself never went to Spain. If that's not creativity and visualization at its best, I don't know what it is. And in this piece called Gollywog's Cakewalk, one of the pieces out of the so-called Children's Corner, a collection of pieces that he offered to his child. Every year the child got a different piece, all the way to the age of 6. Beautiful present, if I may comment on that. On this piece, Gollywog's Cakewalk, Debussy takes something that we also scientists do very often, namely, we never discover things alone, right? We need to quote, we need to cite the literature, we need to refer to what our predecessors have done. Sometimes our colleagues are doing at the same time. And we cite them in our publications, right? This person has before studied this and this and this type of work. And this also happened quite often in the history of music. And in this piece, Gollywog's Cakewalk, Debussy does a direct citation of someone who was probably the number one, the premier musician of his time, Richard Wagner. And why was Wagner such a celebrated musician? Well, he had a lot of good press going on for him, but he also, in the opera Tristan and Isolde, created something which I, as a student of music, learned, a defining moment in the history of music. The so-called Tristan chord is a chord where you no longer sense the typical forces of tonal music. It's a moment where you actually have no idea where the music will take you. This is neither meat nor fish. Where are you going from here? And then he resolves it. From here you know you are there. But at this point, you have no idea what's coming next. And this is actually the very beginning of the opera Tristan and Isolde. This, of course, made Wagner extremely popular in musical circles. Debussy quotes this directly in this piece, perhaps not in the most flattering of ways. I will let you decide by yourselves when you listen to it. But the piece itself has nothing to do with this very intense, charged emotional behavior and character of this chord. It's actually a piece written in pure ragtime. And so Debussy, writing a ragtime, jazzy, American-style piece, finds a way to quote his nemesis in the middle of the piece in terms which, again, I will let you, ladies and gentlemen, decide whether you find them flattering or somewhat mocking. And as we come to the end of today's presentation, I will just finish with a piece that I think does not require much introduction of itself. And it's because it might be getting dark outside, and I would like you all to go home with the power of tranquility. Again, Debussy himself showing us how much poetry and beauty you can extract out of a shining moon in a beautiful moonlit sky. Clair de lune, for you ladies and gentlemen, I hope you have enjoyed today's presentation.